So we have pleasure to have here Melika Payvard from ATH that is going to have an interesting talk about brain-inspired computing from hardware, maybe something on processing as well, learning. So it would be interesting for us to understand also this other field of communication and computing. Thank you very much.
Thank you so much for inviting me. It's a pleasure to be here. So like Paula was mentioning, I'm actually coming from, let's say, a sister field to you guys. I've been looking at the program that you've been having here. It looks like, you know, so, and I also talked to Michele and Paula before. So looks like this consortium is about processing information on the edge, but more from like a machine learning or A&N point of view. I also saw there were some interesting lectures on reinforcement learning and so on, which is super cool. So the presentation here is basically an effort to give you kind of a gist of what this whole field of brain-inspired computing or neuromorphic engineering is about. So I'm coming from Institute of Neuroinformatics. We are part of both University of Zurich and ETH. And so we have this big institute where there's like 100-something people, and there are like neuroscientists who are doing experiments on animals. There are people who are trying to take this information, make models of computation. And then there's the engineering part where we try to kind of understand and take inspiration from these models and build it into hardware. And so this field actually has been around, let's say, for 40, 50 years. And recently, we have kind of found this edge computing niche, well, we as a community, where, you know, because by definition, brain is good for the edge, right? So because we as intelligent animals, we process information, right? And then we act upon the environment, which also kind of fits into this whole reinforcement learning session that you guys had. But by definition, this is an edge problem because we do all of this stuff with very, very efficiently, right? Like we're very efficient processors, let's say. So I am going to kind of give you an overview of the entire field. Hopefully I can do a good job of that. So just the motivation of the state of the art that AI is now everywhere. It's on our watches, it's in our homes, it's basically in IoT devices. And this has been possible through a perfect storm in AI, which has been a combination of a massive amount of data that is available, scalable hardware, and making it available to everyone. And we have some open challenges that as a result of that perfect storm, now we have this exponential growth of data and also the energy that is required to process it. And as you know, and this is kind of what brings our community to your field, is that so the computation is now being moved from the cloud to the edge, because then we can avoid this data movement from the edge to the clouds and save some energy. But what is still unsolved, other than the processing, which people are working on. So basically we want to do this processing on the edge, but also we would like to learn on the edge. And I'm going to also touch upon that kind of at the end of the presentation of how we can not only process information, but also learn in an online way. So like I said, our niche is that we would like to learn more from neuroscience. And the reason is that, so the brain is very efficient. The reason why it's efficient is because, so we have, or the reason we think it's efficient is because, so we have many number of neurons. So 10 to the power of, this should be 10 to the power of 11 here. Yeah. So basically we have 10 to the power of 11 neurons. Each one is connected to some 7,000 synapses. So it just fans out to 7,000 other neurons through synapses. And the time scale that the neurons work is about a millisecond. So basically in every second you have like 1,000 time steps. So you can kind of see this, and this will be about 600 petaflops. So this is, in terms of flops, this would be 600 petaflops. And the brain does this in about 20 watts. So this does this processing the entire power consumption. But the world's most powerful computer can run 442 petaflops at 30 megawatts. So there's like a huge gap in energy. By the way, these numbers, I'm actually also going to have pointers in all of my slides of where I got this information. So this is from Simon Thorpe, who is a researcher at CNRS in Toulouse. And there's like this YouTube video you can go and find. It was a tutorial in International Conference on Neuromorphic Systems 2021 by Jason, which has a lot of the information that I'm going to talk about. So now what our field does is try to kind of learn more from neuroscience, but also kind of bring together the development in multiple fields. So basically we have this algorithms, which are the brain inspired computational models. We have this new memory technologies, which I will talk about later in the talk. And we have the silicon technologies, and we have edge applications. So we try to kind of learn, but also bring together the developments of all of these fields in this neuromorphic engineering field. So what is this good for? So today's processors, just want to see if I can do this. Yes, you see it here. So today's processors, what do they have? I think in all of these computers, right? So we have this processing elements, these PEs. We have like a cache, right, which is closer to the processors, and then a memory, which is usually DRAM, because DRAM is the cheapest memory that's available. That's kind of active. Now, most of the energy, if you look at it, so whenever you do a multiply and accumulate computation, which is basically the core of any neural network computation, most of it goes into memory reads. So you see that the computation basically is almost free. So this processing elements, but most of the energy goes to reading memory. Specifically, if the memory is kind of far away from your processor, it's basically where most of the energy goes. So what does the brain do instead? So brain has these kind of organizing principles. Then one of the most important one is that it exploits sparsity. So, and this sparsity is both in time. So basically it sensors. So the biological sensors only encode information when it becomes available. So it's not continuously just sampling from the environment, only samples from the environment when there's something interesting, which we call the so-called event-based sensing, and only processes this information when the events become available, which is event-based processing.
Sorry, I mean, we have to, maybe not the whole brain, but something has to be sampling continuously in order to know that there is something available. Right?
Yeah, so we get it. What is your name?
Mas.
What is your background?
Communications engineer.
Communications. So basically, it's kind of like a sigma delta modulation. So we'll get there. So basically, if there's nothing changing, you're not going to encode it. So I'll get to the event-based sensing, and if I don't answer your question, we can get there. But actually, by the way, how many people have an engineering background here? Okay, so everybody does. And no one has biological background, I suppose. Okay. All right. So so we also only process information when it's necessary. So we basically generate these events and then we process them. We process them as they become available. And the brain also exploits sparsity in space. So where our connectivity is very local. So the neurons mostly connect to their neighbors and very sparsely to further nodes, because if you want to send information to further nodes, you have to spend more energy. And evolution kind of has found the solution that to only connect mostly to the neighboring neurons. Another important thing is this co-localization of memory and processing, which you might have heard as in-memory computing. How many people have heard of in-memory computing? Okay, so basically there's this field of in-memory computing, other than this brain-inspired stuff, which is since most of the energy goes into fetching data and bringing it, so we can try to make this closer. So it's either like you might hear the terms like near memory computing. So you can basically in some of the accelerators, they do a DRAM read. So once they fetch the memory, they put it in the cache, and then they try to reuse information on the cache. So this is kind of near memory computing. Or the memory itself becomes where the processing is done, which is also what I'm going to talk later. So you avoid this data shuttling between memory and processing units. Also, the brain does adaptation, which is this online learning that I was talking about. So other than processing, you also learn online. So I am going to go through all of these, hopefully, just give you a gist of each of them. So just to give you also pointers on sources that I have used other than my stuff. It's like I said, there's this very nice tutorial from Jason Eshraghian from ICONS 2021. This is the link. Then there is another tutorial by Emre Nefci, who is a professor at Ulish Center right now. And Jason is also a professor now at University of California, Santa Cruz. And then also shamelessly giving you a pointer about this neurotech project, which I have coordinated. We actually just had the review meeting yesterday or 2 days ago. So the neurotech project is basically where we try to kind of bring together all the activities around neuromorphic engineering in Europe together. So it was like a CSA. It's a coordination and support action of Horizon 22 program. And so through this CSA program, we have collected a huge number of tutorials, educational series that basically talk about what is this field about, what are we trying to do, what are the applications, and so on. So in case you're interested, these are very good pointers. So let's go through this first, temporal sparsity. So like I said, we want to encode information only when it becomes available. There are many different examples of these sensors now in our field. So it's like there's vision, there's audio, olfactory, touch, and actually really any real world signal. So now actually you're also working on these biomedical signals. And so, so basically trying to have these event-based sensors that can sense your biomarkers, so like your heartbeat, muscle activity through EMG signals, or even recordings from the brain like EEG signals and so on. But here I'm going to for now focus on vision and audio. So this is a video just to tell you how an event-based camera is different from a normal camera. So in the video, soon you will see that this starts to move. And is how a standard camera encodes this information. So it has to sample, right? So it's continuously sampling from something that is moving, so it can alias, right? So if it doesn't sample at twice as fast as the speed of this guy, it will alias, right? It's the Nyquist rate. But what the event-based camera does is that it's because it has this temporal aspect, it will just create this spatial temporal pattern. And you see when this stops to move, this creates no more events, but the standard camera just keeps creating or keeps giving the same frame, right? Like although nothing is moving, just continuously giving you the same thing. Now, if this starts to move really fast, this starts to even alias very, very badly, but and does a motion blur as a result of that. But this dynamic vision sensor, the event-based sensor, in theory, is supposed to give you kind of this fast stream of spatial temporal patterns. So now let's see how this works. So this is a camera that is inspired by the retina. So the retina has this photoreceptors, this bipolar cells, and the ganglion cells. So this photoreceptor is basically, so each part of this implementation here is supposed to mimic basically exactly what happened in biology. So this photoreceptor has like a log block. The reason why it has a log block is that the dynamic range of light in our eyes is really huge, right? So we can see stuff in the dark, but we can also see stuff when there is a lot of light. And if you have a normal camera, if there's dark, if you see that you need a flash, and when it's super light, it doesn't really capture anything. But your eyes can see it because we have a huge dynamic range. And the reason for this dynamic range is that it just does a log compression. So if if your information is going, orders of magnitude changing from, let's say, 10 to the power of -2 to like 10 to the power of 10, right? This in the log domain, you're going from -3 to 12. So when you do log compression, then you can bring everything to silicon. So this photoreceptor basically receives light, creates a current, and then does a log compression. And this is a capacitor which removes the DC offset. And these bipolar cells are basically what we call a change amplifier. So they detect a change, and as soon as they detect a change, this goes through two comparators in the ganglion cells, and it generates an on or an off event. So this means, and as soon as they generate that, then there's this event reset. So this capacitor then discharges, and then it starts again. So this is why it just looks for changes. So if there's no change, it doesn't create any event. So our eyes were always sampling because we saccade. Do you know what is saccade? Has anyone heard what is saccade? So basically your eyes, even if you're okay, even if you're well, I'm the host, I think I have to admit people because I could. I think. Yeah. Okay. So our even if our head is fixated at a point, our eyes are still moving. So like if you look like your retina every millisecond kind of just moves a little bit to sample from the environment. And if it cannot move, you don't see. And you can trust me on that. Okay, so basically this is how the camera works. So it detects a change in the log current, and then as soon as that change is detected, it creates an event. So this is what we call using delta modulation. So you detect the delta and you encode it. And this is again from neurotech educational webinars. If you're interested to know more details about the camera, you can go and see this. So Toby Delbruck he's at our institute. He's one of the pioneers of the field of neuromorphic engineering, and he's been developing these cameras for 40 years. And so he had a talk there. This is from there. So now let's see how does this work in like some real world case. So you can see here, this is actually INI. This is where I'm coming from, Institute of Neuroinformatics. This is at the entrance of our building. So you can see that, so this is a normal camera. This is the gray stuff, and the colorful things, which is the green and the red, is what the DVS, or the dynamic vision sensor event-based camera, is producing. So you can see of this entire scene, what is encoding is just what is moving in the scene, which is the ball and the hand of this guy. Or basically in the other thing, if this person is playing tennis, and you can see the only thing that it detects, it's what is changing in the scene. So what is this good for? So yes, I mean, the applications are basically object tracking. So when something is moving, you want to track it. For surveillance, it's very good, because you can imagine that you have this camera that is just sitting somewhere. It wants to see what's happening, and it's just continuously processing information where absolutely nothing is happening. No one is there, like it's just there. Every half an hour, one person passes by. There's no reason to be processing that information when there's nothing happening. So that for surveillance, for example, is very good. Can imagine like for autonomous driving. So because other than the power, this DVS camera is also super fast, right? Because it doesn't need to send a lot of pixelated information. It's just sending information of whatever is changing. So then it's super fast. So it's good for like these agents that have to act in the environment in a fast way, which is the case, for example, in autonomous driving. Okay, another example of this is this event-based audio. Yes, please.
Do you think like something similar to the camera can be applied to a LiDAR sensor?
Yeah, sure. Mm-hmm. Yeah, so basically any signal, you would just have to build the front end. You would just have to build the front end, and then detect the change. And of course, then the less the dynamic range, then it becomes a harder problem. What was your name? Marcello.
Thank you.
Yeah. Okay. So we can also talk about now event-based audio sensors. So our ear. So this is basically mimicking the biological ear, which is a mechanical frequency filter. So basically, this is inside a cochlea. So you can see it's kind of this spiral structure. So, and this spiral structure, as let's say a sound wave comes in, it goes through this mechanical filter. So in the beginning, you have these high frequency components, and then as you go more, as the sound kind of travels inside the spiral, it becomes the frequency filter becomes lower. So basically, you go from these high frequency to low frequency filters. So it looks something like just here. So your frequency component is something like, you have these filters here that goes all the way from like 20 hertz to 20 kilohertz, and they're overlapping. So if you want to implement it on hardware, the system block, the system level building block, you have these analog bandpass filters, which then at each, so you can have each of these filters, and in each filter, then you can have an delta modulator. So at each filter, then you see if there's a change in that band, and then you create events when things change in that band. So then you create this cochlea. Unfortunately, you can't hear this because I couldn't make it work. But if you want to see this pointer from Engel's presentation is actually in the University of Sevilla. But just to give you a hint of how does this look like. So this is basically the left ear and the bottom is the right ear. And you see the person is basically saying like 1, 2, 3. And this is encoding that. So you see how the events appear as the person is talking. All right, so what is this good for? The applications are, of course, like basically any keyword spotting applications, speaker identification, speech recognition, but also, for these kind of sensors are very good generally for monitoring, right? Because they are very low power, low latency. For example, for environmental sound classification, like wildfire, security events, medical aid, or stuff like that. So generally for always on monitoring systems. So how about encoding other information, like Marcello was asking, right? So any signal that you have, let's say you want to encode, for example, this, it's like simple handwritten digits. So how can you encode that? So generally spike encoding, so I have been telling you about this delta modulator encoding, right? But you can also just do simple rate encoding, meaning that you have, let's say, this image, and you just go pixel by pixel. Let's say you just have a static image and now you want to encode it. What you can do is also just take the information of each pixel and encode that into a rate of spikes. So the higher the value of the pixel, the higher the rate. And then you basically encode that into a Poisson distributed spikes with high or low rates. So Poisson distribution is basically that the time, so the spike interval between so the time between two spikes are basically random. So this is kind of, this distribution is Poisson, but then you can control the rate. So if you have a high pixel, then it's, let's say, the rate of this Poisson spike is high, but if the pixel value is low, then your spike becomes lower rate. So this is, let's say, one way of just doing spike encoding without doing this delta modulation. Another way of encoding is this temporal coding. So the temporal code is that the information is now encoded in the time of arrival of the spikes in a way that if the spikes arrives earlier, it has is carrying more information or more important information. And if the spike is arriving later, it means that it's not so important. For example, like if the pixel value is high, then the neuron that is encoding it is spiking faster. And if the value, the ones that are black are basically either not spiking or spiking very late. So you basically translate pixel value into a probability of firing of the neuron and the time of arrival, which this is what is called the time to first spike encoding.
I sometimes see the different connections between the since you mentioned at the beginning and this.
Yeah. What is your name?
Yasin.
Yasin. Okay.
What would be the pixels then?
Yeah. So actually, I guess this is a good slide for you here. So let's say you just have now the static image. So there basically I've told you about these 3 ways of encoding. So one is the rate code, which is I guess super simple. What is this latency coding? So the darker the pixel, the later the spike, and the lighter the earlier. Okay. And then there's this delta modulation, which is that if you just take this number 7 in front of DVS, it's not going to encode anything. So it's just going to give you nothing. But if you start to just move it a little bit, then it starts to. This is why I was saying that our eyes do a saccade. So something has to move for DVS to encode stuff. And this is why actually fundamentally spiking neural networks are not good for static signals, because the important thing is that you are encoding stuff in time. So time is an important part of this, event-based processing systems. If time is not there, just go ahead and do whatever you were doing before, because it wouldn't make much sense. Except that some people say that, so this is the real stuff. So some people also say that, hey, look, why do you say that? We don't have event-based sensors, but if you do this latency encoding, you can basically just encode this entire image instead of with analog values with bunch of binary events, and then you just look at the time that they're coming. So there's still benefits in doing this, even if your input is static, because you just reduce the data load, like the amount of data that is required. But basically, if you want to have an entire system, you are really counting on this change in time in the signal. Yeah, so this is a summary slide for event-based encoding. Is there any more questions? Are there any more questions?
Just out of curiosity, this encoding are all happening in
the last one.
the last one. It's like a wavelength.
No. This is like a delta module, delta encoding. So the wavelength stuff comes in the processing. This is just at the encoding part, right? And then for processing, for signal processing, then a lot of people use these kernels and so on. This is, as far as I know, is not what is happening in the brain. So this looks like a wavelet, but it's just the input data. It's just an example of if you have a signal like this. Exactly. So like when the signal is going down, you're generating off spikes like these spikes that you see here, and when the signal is going up, you're generating up spikes.
And you're telling us that what is important in the spikes is just the occurrence time, is not the shape of the spike.
Exactly. Yeah, definitely. So I guess we get there later, but so in the brain, so all neurons create this what is called action potential, right? So the action potential actually looks indeed something like this. But for processing, we just take this as as just one pulse, and we just say that this time is what is important for our processing, and the shape we don't care about.
You can use like a series of data.
Exactly, right.
It's just with the rates including the pixel has a bigger value, you see a difference
here, do you see a difference? I mean, with the data motivation, I mean, probably yes, but if you have a bigger value.
Yes, you do, because so the DVS camera is encoding the change in light intensity, right? So if the pixel has a higher value, it means that there is a bigger change in light intensity, so it creates more stuff. Yeah.
For sound sampling, if there is a periodic sound, would be treated as white noise or would be encoded? Like always the same.
Can you say that again? Sorry, from the beginning. Can you say?
From sounds.
Uh-huh.
If we are recording the wave sound.
Uh-huh.
If there is a periodic noise, like a periodic change
Uh-huh.
in the sound,
Mhm.
would be treated as noise because it's periodic, it's always the same. Or so it wouldn't be encoded or
No, it will be encoded.
would or wouldn't?
Yes, it would.
It would.
So basically, as soon as there is basically that thing that you're saying, so I don't know what kind of sound, but let's say if it's just coming in some band periodically, right? And like every millisecond, let's say, so this comes, and so it comes in the first time, it encodes it, then there is nothing. So the second time when it happens, it detects a change and then it just creates it again. So it will not filter it. So the filtering should be done. If you don't want that noise, then you don't, you put like a band, what is that? A band stop filter. Is that what it's called? Basically, you put a stop filter. Like if you don't want that specific noise in the frequency, then you have to do normal signal processing to stop it.
I mean,
What was her name? Sorry, I forgot.
Yeah.
Yeah.
I'm thinking that we as humans all the time, like if there is a background noise, you stop hearing it, you get used to it, and you think that it is.
Mhm.
And also when you see maybe if there's something like mountain birds, I mean, you don't pay attention to little day changes, like you.
Yeah.
Is there a way to do that?
Yes.
This technology?
Yes. Yeah. So that comes more in the processing part. I actually don't have any slides on it, so I can tell you what happens. So basically, what you're saying is what is called a short-term depression. So basically, every synapse. So this information is coming to a neuron. Okay, and there's a synapse here. And this synapse is not only a value, it's not only a weight. It also has some dynamics. So it has some filters. So it has high pass filters and some low pass filters. So basically I'm kind of like doing a fast forward just for your question, but we have to go a little bit backwards after, but it's okay. So basically, let's say you're receiving this very high frequency events. So there's this kind of low pass filter. So it's basically a train of delta Dirac pulses, right? And then you have this low pass filter, which goes up and then it goes down. So there's this integration with a certain time constant. Then it arrives here and then it starts to do this. And this, so that what the synapse has is that information goes through this low pass filter. And the information goes to the synapse. So this is your synapse. And this does a negation here. So this is what is called a short-term facilitation or short-term depression, sorry, or STD. So basically, the reason why you get used to it is because you have this filtering mechanisms in the brain, which do some kind of inhibition. But we did a lot of fast forward.
Okay.
So if you didn't understand it, it's okay. We can go slowly. All right. Okay. So now, what about the output? By the way, whenever you think that we should take a break,
I think we can continue.
we can continue, but I think so too. Yeah. Okay. So now this was input encoding, right? So we wanted to take some inputs and encode it. So what about? So now let's say you want to do a classification task or a regression task. So we also have to encode the output, right? So what about that? So in the classification, now you have a network, which then we can go through how we can train and so on. So basically you have this black box that is receiving some input events. And generating a bunch of output events. So it just takes some inputs and gives out output. So now what does this output mean? What do we want to get out of it? So this output event, then we can either look at it as a rate code again for classification and say that, I have a bunch of output neurons. Whoever is firing faster, it means that it's the neuron that is representative of the class of the input that is being represented. For example, I have a network here, and then to my cochlea, I am seeing 1, 2, 3, 4, and there's 4 output classes, and the network has to say which one was it. Now I look at these 4 outputs. Whoever is firing faster, I'm saying, okay, it means that it was that class. So then the class that my input belongs to is that neuron that's firing the most. Or I can also do temporal code and just look at the neuron that is firing the earliest, and then say that whatever neuron is firing the earliest is the neuron that represents my class. So this would be like for example, classification. But what about also regression, right? So in a regression, you want your output to give you a specific value, right? So if you train like normal ANNs, you just don't necessarily just want a softmax. You care for a mean squared error. So you want to have a specific value for the output. So then you can either learn a specific rate. So then you train the neuron to just fire at a specific rate. Or you also care for the exact timing of the spike. So you say that, hey, my output neuron has to fire at these specific times. So this will be also a temporal code for regression. So now let's just talk about a little bit about these black box, right? So what is in here? So for this black box, first I have to, take really step back from where we were. What does this do? So, sorry, again, I want to say that these are, you can, for more detailed, you can go again and see Jason's tutorial. But basically, your neuron is, so there's your neuron body has a membrane, and then inside of that cell there's a bunch of ions, and outside of it there's also a bunch of ions, and then there's this membrane that is not allowing these ions to just completely diffuse. And this is basically reminds you of a capacitor, because an ion, it's conductance. So here is conductive, here is conductive. In this membrane is not conductive, so it's basically a capacitor. But this membrane is also not perfect. There's some leak, right? And as a result, there is a leaky resistor, so that you can model that with a resistor. And the neuron, like we said, right, it fires. So at the end, what the membrane does is that it integrating some information. So there's like charges moving, right? When charge moves, it's a current. So it's basically a current that is being fed to this as inputs. And then it just does like a leaky integration, which is basically a low pass filter. And then when this neuron, when this membrane value potential hits a threshold, it just generates an event. So like we were saying here, so it just receives this, these currents, these current pulses, and it just integrates, leaks, and then at some point it hits a threshold and generates a spike. So this is a model, right? So the model, if you look at that RC circuit, so you can write a Kirchhoff's law here. So then you have current coming in, you have the current in the capacitor, current in the resistor. So then you can write this differential equation here. So your time constant is basically the RC, which is this tau, is the derivative of the membrane potential with respect to time, plus this Vm, Rin, and this is basically your reset mechanism. So as soon as you generate an output spike, you reset back to zero, which is like here. So you receive these inputs, you integrate, leak. As soon as it hits a threshold, it generates a spike, and then your membrane resets. So you can model this generation of a spike with this heavy side function. So basically you're usually zero, and you're only one with this membrane becomes the threshold. So this is basically a continuous model. But now if you want to model this in your computer is not a physical system. It cannot do, continuous variables because it has your computer has a clock. So what it works with time steps. So you can also make like a discrete model of your neuron whenever you want to write a computer program that runs spiking neural networks. And this discrete model is basically that you have this membrane potential at time t. And then at time t plus 1, your membrane potential at time t plus 1, so one time step after, is a beta value times your previously, which is basically your decay. So it's this leak, right? So at every time point, it's a little bit less than the previous time step, plus an in if you receive an input. Right? And then you can apply a heavy side function to this. If at time t plus 1, then it becomes a threshold, you generate a spike. And therefore, if you generate a spike, then your membrane potential has to go to 0. So at the end, this is the discrete model of your neuron. So your membrane potential, the value of the previous time step, plus some input, and the input is basically the weight times the input spikes, minus if the neuron generates a spike, which then it resets. So basically, this is a leaky integrate and fire neural model, or LIF. Are there any questions? Yes.
If you don't have a decay, what is the law? What will be this?
So if you don't have a decay, you can't encode time. Do you know why? So if you don't have a decay, what was your name? Aria? So I'm going to tell you that if we don't have a decay, these two spike trains are the same to the neuron. Do you agree? Right? So because if there's no leak, 2 is 2. Right? So basically there is no temporal encoding. Okay.
But only if I decay, so if I don't get information, I will lose the memory.
Exactly.
There
Yes.
should be a way to refresh this memory that I have.
Right. So basically the point is that if you don't spike, so you will lose it if you haven't spiked. And if you haven't spiked, it means that that information was not super important or it wasn't very high because the neuron ignored it,
So
basically.
we can't forget things from the past if you don't have it.
Right.
If you don't go to refresh.
Right. Exactly.
But we are remembering things that we maybe they are important, but we are not thinking about them. I mean, there should be some background process.
Yes. So there's a lot into it. We get into the spiking recurrent network. So basically we have this recurrency. So basically the memory is 2 types of memory. One is a working memory. One is a stored memory. Exactly. So a working memory is basically what your content's continuously thinking about, but is not necessarily a stored memory. So for example, I give you I tell you a sequence of numbers like 7, 11, 13, 15, 2, 2, 1, 3, right? You forgot what I said. No? Now, yeah. Okay, well, you can't repeat the sequence I said. All right, you have a good working memory, I guess. But basically the point is that it's not something that is stored in your memory. It's something that you
It's gone now.
right, it's gone now, right? So it keeps in your head for a very short time.
And then you can consolidate that.
Exactly, but if you keep saying it like a phone number, then you start to actually remember. Hopefully. Okay. So now how can we train these networks? So let's say now this is like it's our neural model. Now we want to train these to do something useful. So there are different ways of training spiking neural networks. One is just to convert your good old ANNs to SNN, which then I can tell you how can we do it, but then there's some problems with it, which then I will also tell you. Then you can also do some unsupervised learning. So without any labels, you just cluster this information without labels. Or you can do supervised learning on this native spiking neural networks with labels. So this last kind of part is relatively new in our community, and like basically 5 years. And since this last part has come to the picture, there's a lot more interest and potential into actually training spiking neural networks to do something useful. So let's just start with converting ANNs to SNNs. So this actually the source for this is Bodo's work when he was at the Institute of Neuroinformatics working with Toby Dilberg and Shichi Liu. So the basic principle is that the firing rate of spiking neurons should match the graded activation of analog neurons. So basically you have, this is your ReLU, right? So this is the activation of your ANN. So it's ReLU, so you find the maximum between 0 and a weighted sum of your inputs and a bias. And then this is now your spiking neuron. So you have this output, which is basically your function activation function is basically this threshold thing, right? So it's a weighted sum of your input spikes plus also some bias, and then you apply this V threshold. Now, let's see how can we go between these two. So, like I said, the basic principle was that you basically copy the firing rate. So how can you convert biases? So bias is basically something that's continuously being applied to the neuron, right? So you can model that as a constant current that is being applied to your spiking neuron. But then there's, one source. Then when you want to do this conversion, there's a source of approximation error, and is that the neurons are restricted to in the simulations of your spiking neural network, the neurons are restricted to a firing rate between R and 0 and R max because it's time stepped. And ANNs can have any value. So basically this is a discrepancy. So what you can do is to do some normalization, do weight normalization in a way to avoid this approximations. So if you want to make it work, so you can do this kind of transformation from value to firing rate. But then there is a source of error, which is that ANNs can have any activation, but your spiking neuron can have a maximum R. So then you do some weight normalization. And Bodo has shown that so this is on he benchmarked this on CFAR10 with basically rate-based encoding, and you can see that with default, so without doing anything. So basically that it doesn't solve the task. You have some 80% error, but when we introduces its normalization, the error goes to some 12%. So this was in 2017. But this ANN to SNN has some shortcomings. So first of all, is an approximation, like I was saying. Then the temporal aspects of spiking neural networks are not at all taken into account, right? So you're basically treating it like an ANN. And if you want to do a better approximation, then you have to generate a lot of spikes because you have an analog value. Then you want to move that into a rate of spikes, and then you would have to generate a lot of events and spikes. So that's not a very energy efficient solution anymore. And of course, it's not biologically plausible. This is not a problem per se, really on its own, but basically means that there must be a better solution to this problem, right? So how can we natively train spiking neural networks? So we can now go to unsupervised learning. So for a very long time in the spiking community, spike timing dependent plasticity is what a lot of people were using to train spiking neural networks. So the main idea is basically that this is a Hebbian-based plasticity or Hebbian-based learning. So the neurons that then wire together is probably something that you have heard about. So basically in these experiments, they were showing that you have two neurons that are synapsing each other, and then you stimulate both of them, and then they start to this synapse between them strengthens in a way that if you remove the spiking from then one of them and just stimulate only one of them, the other one will start also spike, which means that the connection between them increased. Also, there's this very famous experiment by Bain Hu in 1997, which was published in Nature, which what they found, so this y-axis is basically change in the weight, and the x-axis is t pre minus t post. So pre is j and post is I, and this is tj minus ti, so t post minus t pre. So they showed that if the presynaptic spike happens before the post, it means that the presynaptic spike was a causation of the spike, and as a result, the weight between the synapses increases. And this has a time window. So if the pre-spike comes within this time window before post, it means that there is some real correlation between them, so the weight increases. And if the post fires before the pre within a certain time window, that means that the pre was not a reason for the post to fire, and as a reason that the weight between them should decrease. So this is what is known as STDP, or spike timing dependent plasticity. So as you can imagine, this is an unsupervised learning scheme, right? Because what it only cares about is the spike timing of the neurons. So it finds basically correlations in the input. So it clusters the input, because all it does is to see. So let's say you have a bunch of neurons, you give this input, bunch of them fire at the same time, and then they start to correlate, and then these kind of correlations create this like clouds or populations of neurons that are highly correlated, and as a result it creates this clustering scheme, which kind of looks like K-means. So basically so you have this population of neurons that at the end are super correlated. So each one of them fires, the other ones do, and so then we can say that this input, for example, has this many clusters. So one characteristic that it has is that it learns online. So it basically, as the input is coming, the weights are changing, and as a result, it's kind of online learning. So when we say online, we mean real time. So it means that you don't have to have a stored data set. You can just information is streaming. As it's streaming, the weights are changing, and then you can just at the end look at how the output looks like. However, this is a greedy algorithm. What does the greedy algorithm mean? It means that it creates positive feedback. So as soon as two neurons start to fire together, their weights increase, right? And then from there, it just keeps increasing, right? Until it cannot increase more. Because when two things start to correlate, then as soon as any one of them is activated, the other one is also activated, and as soon as they're activated together, the weight between them increases. So the system just kind of completely, the weights kind of bang to 0 or 1. So it's a positive. It creates a positive feedback. There's also this kind of other version of STDP, just for your information, which is a more hardware-friendly implementation of it, which is that instead of looking at the time of the spike, we can whenever there's a presynaptic spike, we look at the membrane potential of the post, and if it's higher than a certain value, we increase the weight, and if it's lower than a certain value, we decrease the weight. But this also has the same problems of STDP. So how can we kind of make this network more stabilized? Basically, you have this network of neurons that are connected, and now you have this local learning mechanism that is just driving it in a positive feedback way. Now, how can you control this? So in the brain, as it turns out, there is this mechanism called homeostatic plasticity, which creates this negative feedback loop to control the firing rates of the neuron, so that they don't go completely either firing a lot or not firing at all. So basically how it works is that there is this, network of neurons with this kind of interneuron. So there's this neurons with this interneuron, which does inhibition. So what it does is that if there is this target firing rate that neurons like to operate at, so if the firing rate of any neuron in this in the network is higher than a certain amount, they try to lower the activity by doing some inhibition. And if the firing rate is lower than some amount, they try to increase the activity. So kind of to move the activity of the neurons within this target firing rate. And the idea is that you want all the neurons in the network to contribute to the computation. So you don't want only one neuron to be super active and some neurons not to be active at all. So you want to kind of use all the neurons for computation. So if you combine this STDP Hebbian learning, which basically is doing correlation with the input, with this stabilizing network, people have shown, including us, that you can do some sequence learning. It's not very easy to do, like I've written here. It's not a very scalable solution. Like none of these super bottom-up, biological mechanisms are super scalable for very big problems. But we have shown that we can learn sequences of, for example, like for counting tasks, we can count a series of numbers with this dynamical network that is as a result of this Hebbian plasticity plus this stabilizing mechanism. And this can be also applied online, so it can be done in real time. Maybe now we can just take a break.
Before we do the thing, what I understand is that both competition is important to make things happen. You also have some competitive advantage.
Right.
So I'm wondering if this is using competition somehow, and what this is happening.
So the competition happens. So it's basically like this K-means algorithm that I was kind of mentioning. This is this competitive. So let's say you have these kind of this is your feature space.
Yeah.
And you have these data points.
Yeah.
And now you have these neurons whose weights are representing these centers.
Yeah.
So then with each data point, these neurons have to compete of who this belongs to.
Yeah.
And if, for example, one of them wins, then the weight by STDP changes in that direction a little bit.
Okay.
Then you present this one, and now these two have to fight. And then it becomes, for example, this is the winner, and then it just moves a little bit this way. So basically, then this just keeps happening until at the end, you kind of end up, for example, let's say with this mean cluster, this mean cluster, and this mean cluster, which is basically the weight of the neurons, and then you end up with these clusters. But what I was saying is that if you just have STDP, at the end, this becomes one big cluster because you cannot separate these clusters from each other. Everybody starts to correlate, right? Because if you have nothing that stops people clusters to correlate, it's kind of like you have like an oscillator that is very dominant, and at the end, everybody starts to oscillate with that frequency, right? Everybody locks into that, unless you have something that kind of separates them, like this negative feedback mechanism that just doesn't allow that to happen.
It seems like it was self-organizing maps.
Exactly. Very similar to self-organizing maps, but not exactly
No.
like self-organizing maps.
Would you suggest we use this type of learning strategy or your type of?
No, I don't suggest. Maybe off the record. Yeah. I think that the one that comes after is basically what is the most rigorous and like systematic way of training spiking networks, which is coming.
Okay.
Marcello. Yeah.
Okay, from an implementation point of view, if you have to implement this, I think you have to complete the pairwise systems. Because you have to choose the two closest ones and then look at it efficient, right? So it's not really efficient if you have more than, I mean, in this case, you have only 3 neurons, right? So only the centroid can be, and you can have multiple neurons. You have 2 sets of, you have the neurons and the data points, and you have to compute the pairwise density. So
no, so you don't do that actually. That's very nice to do. Maybe I can actually
do it later.
No, we can just do it now. It's fast. So basically, actually, it's very beautiful. It's like a mechanism called winner take all. So basically, what you can do. So like I was saying, let's say your encoding is the temporal code, and what you want to do is that you want the winner neuron. So in this case, so for example, whoever is winning, to be the one that fires earliest. So what you can do is that you can have this, what we call an inhibitory neuron. So inhibitory neuron means that it receives a positive input, but then it gives a negative output. So this inhibitory neuron wants to shut down everybody, right? And then everybody connects with a positive input. Okay. So now let's say whoever is winning is going to fire the fastest. So its firing comes earlier. It's going to stimulate this inhibitory neuron, and the inhibitory neuron will shut down everybody else. So basically with one spike, you have determined who is the winner, and that one is the one whose weight is going to change. So it's not like a pairwise comparison. It's a network winner take all based comparison.
It is unsupervised.
This is unsupervised. Yes.
It makes sense.
Maybe. So let's start. Is there anybody else outside? No. All right. Okay. So let's now move to this native way of training spike neural networks, but in a supervised way. So we're going to touch upon this what is called a surrogate gradient, which is an approximation to backprop. And also, if we have time, we can touch upon error-based online learning. So to train these networks with backprop, let's just first go back to this neuron model that I was mentioning before. So basically, this is this discrete model that we discussed. So you have this membrane potential at time t plus 1, which is a beta, which is less than 1 times the previous time step plus some input, and then you apply this heaviside function. And basically your membrane discrete model ends up being this last expression there. So this, if you look at it, right, this can be represented basically as a recurrent connection, right? So this is now, you can look at this connectivity graph. Each one of these is a different time step, right? So the first one is time step 0. You receive an input. You update your membrane potential, you see if this is higher than a threshold. If it is, you generate a spike, and if not, then it's basically getting multiplied by this beta to the next time step. The next time step, if there's an input, it gets the input, it gets the beta version of previous time step, which gives you the membrane potential at time step 1. Again, you see if there's a threshold, passing the threshold. If it is, then you have this spike in time step 1 and so on. So basically, you can represent this LIFT neural model, the leak integrated amplifier model, as a recurrent neural network. So if you can represent this as a recurrent neural network, then the question is, can we use backprop to train it? The backprop through time to train it, right? We use backpropagation through time to train every ANN. So maybe now we can also use BPTT to train this spiky neural network. So the first thing we have to do now is we need a loss function, right, to train this. So like we were mentioning, one thing we can do is to first count all the spikes, right? And we want the class that represents we want the neuron that represents the class to have the maximum firing rate. So then we can use cross entropy loss by maximizing the current class spike rate and minimize the rate of the incorrect spike rate. So this is basically rate code. We can also do MSE loss, so mean squared error loss. So we set as a target spike rate, and if there's an error on this target spike rate, we update the weights, and if it's not, then we have learned. We can also do a mean squared error on the membrane loss. So which is basically the temporal code that we were mentioning, right? So basically you have this pulse train that you want to match to the output spike. So you want to match the membrane potential at each time step. So you're kind of managing or micromanaging this membrane potential at each time step, and you do an MSE loss on that. And the great thing is that, so now you have this loss function, right, that you're training, and you can also control the sparsity. You can add this basically L1 sparsity regularization to your loss function, and then you say, hey, I want this much sparsity for my neurons in the network. So this is basically how we can define loss. So now, how can we actually do backpropagation? So let's say we have this cost function L, right? That we have now defined. We just defined our loss. So now if we want to do backpropagate this error, so let's just look at one time step for now, okay? So at one time step, we can write this as a chain rule, right? So we have this, we can write this chain rule in this chain. So we have this derivative of loss with respect to the spiking output, derivative of the spike with respect to membrane potential, derivative of the membrane potential with respect to this I input. And this I input is also basically, it has a weight, right? So each input here, there is a weight associated with it, which is actually coming from the input. So then you can write down this as the multiplication of these 4 terms. So this first term is basically your error, depending on how you define your loss, right? So if you define your loss as a spike rate, this will be how much is your output neuron firing rate is deviating from the target firing rate, or if you define the cross entropy loss, it will be basically the error in that. So the first term is basically error. This third term is basically 1, because if there is a direct relationship between I and V. If you increase I, you increase V linearly. It's an integration, right? So this third term can basically almost be ignored. And the last term is basically your input, right? So you have this I, the derivative with respect to your weight is basically your input. Okay, so now we have error and input, and there's this term left, which is the derivative of the spike with respect to the membrane potential. Now, this has classically been the disaster of training spiking neural networks. Why? Because this transfer function, which is the spike versus the membrane potential, is a non-differentiable function, right? So you basically, as soon as you hit the threshold, you goes up. So it's the heavy side function, and this is not differentiable. And for years, the community was just hung up on this point. So then there's some smart fellows like Emre and Friedem and Zenke and many people in the community said, okay, I mean, it's not so important that this is kind of, as soon as it hits, it jumps. It could also be like a more smooth function. So which then makes this which then has a derivative. So you can make it differentiable. And basically how it will be is that you are kind of approximating this loss landscape, which is more discrete because you have this spikes, to something that is a bit smoother in the parameter space. And what we do is that when you're training the network, in the feed-forward model, when you're evaluating the spiking network, you actually just use the actual spike activation function, which is the heavy side function. But when you're doing a feedback for learning, you're going to use a surrogate function, which is just basically this guy here. Okay, so basically this is what we can do. But like I said, this was basically for one time step, right? So we just took this one time step. We said we applied the chain rule, and that ends up basically being error times input times the derivative of the surrogate function. But what about going back in time, right? Because we said that this is a recurrent network, right? That we have to now go back in time. So if you want to go back in time, then what we need to do is basically, okay, so you have this chain rule here, but then you have to go back at each time step and pass through this beta, beta, and beta, right? And so the derivative of the membrane potential now in time step t plus 1 with respect to t is always this beta, right? This is what we said. And the further back in time we go, this beta, we're basically multiplying this each time by beta. And beta was a value that was lower than 1. So that means that the further back in time you go, then your gradient vanishes, right? So it becomes 0. So basically you have almost like a kernel function, right, which has this exponential decay right, because like beta time to the power of n. And interestingly, actually, maybe this looks a little bit like the SDDP that we were saying before, right? So there's like this window of time that is important for learning, and after that it's basically not important. So in order to train these neural networks, then these spiking neural networks, we can rewrite this in the form of a recurrent network, use backpropagation through time, do a surrogate gradient approximation, and then apply this kernel in order to go back. So there are now these GitHub repos which do train spiking neural network based on this. You can use, for example, PyTorch even to train it. So in PyTorch, you can just write your equations, and you can use the auto differentiation. So the only difference is that now in the backward path, you just have to do an approximation to the surrogate function.
Okay.
So if you're interested, I can also send you these repos that are available from different people in the community, and basically you can just immediately hit the ground running on training spiking neural networks. So yeah, yes, please.
The data is by nature smaller than one, so we don't have that to be present.
Yeah.
But this, by this assumption, in lighter disk, this is limiting the window.
Yes.
of propagation, right? Because beyond a certain number of steps in the path, it becomes useless.
Right.
So in a standard setup, let's say the neural network window, we call it vanishing gradient, because the gradient will be vanishing to the fact that this one will be going down. But here it's not like a negative effect. So it's like something that we accept, right? We don't have to go around and to modify something.
No, right, exactly. So what I want to actually say here, exactly. So if you need more time, so basically, let's say now you were processing this, and like I said, this window of time is limited. But what I want to say is that in the network architecture, this is now a feed-forward network. Although we are representing it as a recurrent network, this is a feed-forward network. So a feed-forward spiking network has intrinsic memory, which is this much, right? So some of the inputs that you usually need a recurrent network to process for a spiking neuron, you can just use a simple feed-forward network. Now, if you need more memory for longer sequences, then you need to have a spiking recurrent neural network. So you add another recurrence in this graph, and that can provide you with more memory.
And how you train that?
So basically, it will be the same way, right? So it will be again backpropagation through time, but just your graph will be a bit different, right? So every one of these will go back to itself. So you will have another connection here at each time step to itself, right? So you will have sub connection.
You have a nested propagation.
Exactly.
And this is done.
Yes. This is in the repos that I can share with you. This is all done. Yeah.
And also, when you define the recurrent neural network, you may have a problem of the vanishing gradient.
Yes, I mean the same problems basically exist.
Okay.
Right. So the thing is that sort of so ReLUs kind of solve this problem a little bit, right? So then you can also a spiking network is activation function is basically almost like a ReLU, you can say. So the same thing applies here, except that now there's a little bit more memory just because you have this stateful computation, because your membrane potential basically has memory by itself already. But you can introduce sparsity, but the rest of the stuff, everything applies.
So you can also define convolution on things.
Yes, so there's convolution, spiking convolution on neural networks. So that becomes basically the network architecture, right? But so you can really directly just replace your neurons with the spiking neuron and retrain the spiking neuron natively. Actually, I will show some examples that we have used spiking convolution on neural networks to do scene classification. So everything is about basically this computational graph and how the connectivity of your network and the network architecture just changes this graph. And then the rest is backpropagation through time, just with this trick of basically surrogate grading in the feedback.
And this gradient approximation is actually acceptable. Is that the price that we have to pay
Yes,
for that?
the price is that it's you cannot do super deep, and so this kind of applies for maximum 4 layers. Yeah, and after that it's so. For example, as far as I know, ImageNet level has not yet been solved. For example, with these methods, it's really more for edge applications for now.
Okay, yes, for us.
Okay, so also I want to kind of touch upon a little bit about the processing side and implementation of the processing side of these spiking networks. So, like I was saying, we have this concept of in-memory computing. So basically, the idea is that you have this memory block. So this is a memory block, and this memory is storing the weights of your neural network. And now what happens is that we have these events that are, for example, let's say coming from your event-based sensor, and we do some kind of decoding here, and the spikes kind of get delivered to these columns, and then you do a memory access, so you read the memory. So basically, as soon as there is an event, you access the memory, you read the memory, and the sum of the product of this input now with the memory is summed on these rows, which are terminated by these spiking neurons. So these neurons now integrate this information. As soon as they hit a threshold, they generate events. And then we encode these events and we send them out. So these systems are basically event in, event out. With doing the MAC operation in situ inside the processor. So this is why this is called in-memory computing, because this MAC operation, the processing is really done inside the memory. And then you can also have these recurrent connections, like I was saying. So basically, you have this feed forward from the input, but you can also have these neurons feed back, and then you have this recurrent matrix of weight matrix. Basically, this means that neuron 1 has this connection to itself, neuron 2, and so on. So this will basically implement this spiking recurrent neural network. Now, what is basically good here is what I was mentioning in the beginning of this, that so now we have this power efficiency because it's data driven and sparsified, because it has this in-memory computation, so you're not shuttling information between the processing and the memory, so everything is in the same place. And we argue that this is now more memory efficient. Why is it memory efficient? Because we have this dynamics, like I was just now mentioning. If you match the dynamics of your input, for example, your speech, to the dynamics of this neurons, for example, you create these match filters which enable real-time computing, which means that your processor is not too fast, because if it's too fast and your signal is too slow, that means that you before your information is coming very slowly, but your processor is super fast. So then the processor either has to sit idle, or you have to store this memory for it to see the entire sequence. But if the processor time window is really the time window where the information is being presented, you have this match filter that can do real-time processing. And as a result, these systems do not require a cache or a buffer. So you don't need to buffer data. You can just, process information as they become available. They also have low latency because what you now need to process is basically just a bunch of events that are being available, and you don't have these, big like vectors of analog information that are being represented to all of these columns. At every point in time, you just have these sparse events that arrive at each column, and you just process those, so your latency goes down. And we can see that hopefully, if we have time, we can do online adaptation with these. So the community of neuromorphic systems have developed these two parallel world of digital signal processing and analog. So that they both of these kind of digital and analog world, they all follow these 4 points that I was mentioning in the previous slide. So they're both event-based. They do parallel processing. They all have some kind of dynamics because your neuron basically is stateful, so it has to have dynamics. They all try to follow some kind of in-memory or near-memory computing, and they try to have online adaptation. So, for example, an example of these digital systems is, you might have heard the IBM TrueNorth, which is one very famous one. Intel Loihi, which is from Intel, and they have created this entire community of INRC, which is the Intel Neuromorphic Research Community. If you're interested to work with their devices, you can actually just send them an email, just propose a project, and they give you a remote access to their neuromorphic chips for free. There's also this Spinnaker, which is a result of the Human Brain Project, which is a combination of these ARM processors. So these parallel nodes, computing nodes, are basically these ARM processors. It's a little bit more like to the conventional side, but they do kind of local digital processing and global spiking computation. And then there's this, let's say, more brain mimicking the brain, or more biomimetic side, which is the analog neuromorphic chips, which basically do everything that the other ones do, but in analog. So like I was mentioning, we have this LIF model, and if you want to implement this leak integrate amplifier model, which basically is an RC circuit with some kind of thresholding, if you want to implement this on your computer, the computer that cannot do this in a continuous manner. Like you have to do some kind of time step. So what the analog systems do, they just try to create really that RC circuit for you on hardware. So now your hardware is no longer a computer, but a substrate that is implementing the algorithm for you. So now the algorithm and hardware are one thing. So that's what is more like the brain, because your brain, is not time stepped. It's you're basically a bunch of filters and bunch of comparators, and that is what really the analog system tries to do. So tries to create you a hardware that is the algorithm itself, and that's basically what my research is mostly focused on. Specifically, what I work on is these kind of more emerging memory technologies. I don't know if have you heard about these resistive memories, memristors? Yes. How many people have heard about them? Okay, some like half of the audience. So for those of you who might not know, so these are like resistors with non-volatile memory. So they usually consist of a top and a bottom electrode, which is conducting, and there's a switching material between these two top electrodes, which let's say in one case it's an oxide that has some deficiencies. So these deficiencies act kind of as an ionic charge. So when you apply a field across these top and a bottom electrode, these ions start to move, and they create what is known as a conductive filament. So basically, you can imagine that you have now two electrodes, and the two electrodes start to have a path between them, which causes the resistance to drop. So electron can pass freely. So in a binary sense, you basically have a memory that is either not conductive because there's no conductive path between the two electrodes, so no electron can pass. But when you program the device by applying a large field, these ions start to move, you create this conductive film or filament, and your electron starts to move. So basically, it's a non-volatile memory. So when you remove this then programming, the ions kind of freeze wherever they were, so it creates a non-volatile memory. Like the great thing about these devices is that they kind of check out all of these requirements that we were talking about before. So they enable this in-memory computing for free, because what you can do is that you have these inputs. You can map your inputs to a voltage. You have the weight, which then you can map into the conductance of these devices. And then through Ohm's law, you get voltage times conductance, right? So this current then that comes out of the device gives you already a multiplication. And then through Kirchhoff's law, you get a summation of these two multiplications. So basically, just by virtue of Ohm's law, you get a Mach operation. And that's why we say the memory is doing computation. So you just have like let's say a matrix of these resistive devices which have memory. You can change each of them to high or low conductance. You apply your input as a voltage, and just by virtue of Ohm's law, you get a multiply and accumulate computation. So your memory is doing computation, which is what in-memory computing is. These systems work very well with events or spikes, because in order to read from these devices or write from them, you have to apply an electric pulse anyway. They enable this massively parallel processing because they are very small. So you can see here an example of a device that I work with. This is from CTTC in France. So they implement. So this is a 130. Yeah, you guys. Yeah, okay. So you're from List. Okay. You're from Leti. Okay. So I work with Elisa Vianello. I don't know if you know her. She's the head of the edge computing lab actually at Leti. Okay. Yes. So basically they have this 130 nanometer, so this is from 130 nanometer process. So they take, so SD has maybe Thomas can tell us more about it. So basically, there's this SD microelectronics. So they take they do the CMOS process up to layer 5, and they send it to Leti. Leti implements and grows these devices between metals 4 and 5. So you can see here, they basically put this layer of RRAM, which is the oxide, which is the hafnium oxide. Here they grow this, and then they put a metal 5 on top, and they send it back to SD, and SD completes the process. So basically, the point I want to make here is that you can do this 3D integration, right? So your memory is not going to take silicon real estate, but it's growing in the third dimension, which is what is very promising about these memories, because then you can have a very dense memory array with the CMOS without taking real estate from CMOS, which is very expensive. These devices also have some internal dynamics, and they adapt, which then maybe hopefully we get there. So we have implemented, for example, this in collaboration again with Leti. How many of you have electrical engineering background, like circuits? Okay, very few. So
Many years ago.
Many years ago. Okay. So maybe I don't tell you like about the details of this, but basically what you can see is that we have these devices in parallel with a transistor. How many know how does a transistor work? Okay, all right. Okay. So you apply your events basically arrive at the gate of these transistors. As soon as an event arrives, this transistor starts to conduct. And this voltage gets applied, for example, at the bottom voltage here. The other side is pinned by this amplifier. You can ignore how that works. But basically, point is that as soon as an event arrives, you apply a voltage across this device, and you create a current, which is proportional to the value of this conductance. So basically, that current now is giving you a multiplication of your inputs with the weight. You feed that into this block that gives you dynamics, and this is basically an integrate amplifier neuron. So these devices, so one device, so this is one very important thing about these devices, is that so in your DRAM or SRAM, one device has one bit of information. It's either on or off. But these resistive RAM, you can get multiple levels out of it. So for example, this device, this is a statistical measurement from 1,024 devices, or I think, or 4,096 4-kilobit array, that shows that this has 8 levels, right? So the conductance goes all the way from 40 microsiemens to 120. And so one device gives you 3 bits of memory. And that translates to this dynamics, to the peak of this dynamics. So the higher the conductance, the larger the peak of the current, which then results in the neuron to fire more. So here basically is the y-axis shows you the firing rate of the neuron. The x-axis shows you the RM conductance. And as the conductance increases, which means your weight increases, your neuron fires more, which is basically what we wanted. Now, if we can take these systems and apply that to some real-time sensory applications, which is what I promised you all along. So, for example, we have applied this to heartbeat anomaly detection. So we've taken this this open access data set, which is this MIT VIH ECG. We have encoded this into spikes using delta modulation. So the encoding that I mentioned in the beginning. So basically, when there's a lot of change, you create a lot of spikes. When there's no change, you don't create any spikes. And we have applied it also to this speech recognition data set. So this is a data set between 0 to 9. This is actually, it's an event-based data set, which has been collected with a cochlea. So it's both in English and German. There are people that are saying 0 to 9, so it has 20 classes. So basically, this is anomaly detection, just 2 classes, binary classification, and this has 20, so 1 order of magnitude more. So you can see here the type of classifications that we've gotten with this RM. I want to bring to your attention one thing before is that, these devices, although they have, one device now has 8 bits, 8 levels, so 3 bits, but it's not your, lovely 32-bit floating point that you get on GPU and CPU. Your memory only has 8 levels, doesn't have 32-bit level. It's not 32-bit, it's 3-bit. So that gives you a large constraint for running this on hardware. And I'm sure it's also the case for all the accelerators, actually. Okay, so here, just the MNIST also handwritten digits, just as a reference here. The ECG classification gives you like 90% accuracy, and the SHG with 20 classes is giving you like 70% of accuracy. But what I also want to bring to your attention is that if you have some bit error rate in the memory, just because, for example, some of your devices are not working. Thomas can tell you, sometimes these resistive memories, they don't work as, are you working with a resistive memory? No.
No. I don't.
You don't?
No.
Okay.
How is it?
Okay. So basically these resistive memories, or also any memory, but specifically resistive memory because it's not 100% mature technology yet. So sometimes, you want to program them and they don't get programmed, like you apply a lot of current, nothing happens. Or that your because of the fabrication somehow ends up that a device you cannot turn it off. It's just on, right? And this is kind of a yield problem. But you can see here that these the network is tolerant to some 10 to the power of 3 minus 3 bit error rate. And after that, it starts to fall. But if you do know from your batch which devices are not working, and you introduce that to your network, then of course you can retrain it and get your accuracy back. But what I want to also bring to your attention here is the memory and energy footprint for these two tasks using these spiking networks, because, again, all along I've been telling you that these systems are power efficient. Just want to tell you what kind of numbers we're looking at. So for this is the memory footprint. So let's say for this more difficult task, which is this speech recognition problem, you need about 100 kilobits of memory. And about 30 microjoules of energy for one for one trial. So when you say 1 or 2 or 3, it's basically 30 microjoule per classification using a recurrent spiking neural network. Okay, so that kind of ends this temporal sparsity part of the presentation. So
the signal, you're not using the sample for the condition, all this stuff is, in the standard processing for the signal, what we do, we have the data on the mind, and we transform it through the sample coefficient. So this is a feature stuff. Before applying the
yeah, this doesn't do that at all. No.
You do it on the raw data.
Exactly. So basically, the processing that is done is really just this filter banks that I was mentioning in the cochlea. So it has this filter banks, and in this filter, so you basically. Yes. So the cochlea itself does kind of a pre-processing in a way, right? So they do not have the same band. No, they have overlap. They are
larger, low frequency, and they get
exactly. Exactly.
Same thing that we do with the substitute.
Exactly. It's the MF. What is it? MFPC. Yes.
So they do this in a signal processing way.
Exactly. So that part is similar. So inside the sensor, we have those. So that's kind of the sensor.
This is the processing that we do in the digital.
Right. In the analog. Exactly. So the part that it becomes digital is the events. And then as soon as those events are generated, then we do event-based processing. But yes, it's similar to that.
Maybe you already said it to the comparison to digital years. What you mentioned the first slide, energy efficiency is 2 orders of magnitude better. Can we compare this
to conventional
and see?
Yeah. So I get that for this specific task, the state of the art. When I talk about state of the art, I'm already talking about keyboard spotting ASICs. So because there's different state of it. So if you compare this to CPU, for example, then it's orders of magnitude. I will show you a slide on that. But also conventional, but there's also these kind of ASICs that just do keyword spotting. So for example, if you look at ISCC, every year there's like these IoT session, right? And they just do ANN accelerators specifically for speech. And compared to that, this is a little better, but not a lot better, because those are also highly engineered systems, right? That is beaten for performance. And you have to take into account that this is, done by 2 PhD students that have not done that optimization. This, the performance gain is really just coming from the sparsity and the SNN architecture. Now, if you really design an ASIC specifically with, information tricks with this, I cannot give you a number of how much gain that would be. Yeah, what I can tell you is that without doing a lot of effort, just having, PhD students doing, crappy chips, this is already giving you a lot of gain in.
We're almost all PhD students.
No, what I mean, at ISCC, there are like these big companies, like, I don't know, Toshiba. I guess you guys also have a partner at Toshiba, or like, Samsung, these are like big companies that have team of engineers that do this, right? So it's not really comparable to something that you do at an academic setting. Are there more questions here? All right. So I also told you that brain not only uses temporal sparsity, but also uses spatial sparsity, right? So the neurons like to connect mostly to their neighbors. So if you look at the connectivity matrix, for example, this is from a functional MRI, actually from the human brain. These are like actually regions. You can see that. So the black means there's no connectivity. And the more red it gets, it means there's higher connectivity. So you can see that most of the connectivity is in the diagonal of this matrix, meaning that most of the connectivity is with the neighbors. So neurons are connected to whoever is closest to them. So now if you want to, let's say, we want to do brain inspired stuff. So let's just map this connectivity matrix into this crossbar array that I was telling you about. Oh, sorry, I forgot to say that basically this kind of connectivity that is more local gives rise to what is known as small world graphs. So small world graphs are these basically graphical models where you have large clusters. So you have a large clustering coefficient. So you have these clusters of neurons. And you have short path links, meaning that from every node in the graph to any other node you want to go, you can go fast. So it's not only local connectivity, but it's sparse global connectivity, which gives rise to this short path link. So if we now want to map this to this crossbar array, that means that, for example, your neuron 1 is connected to its neighbors, let's say itself and neuron 2. Neuron 2 connects to neuron 1 and 3. Neuron 3 connects to, also its neighbors and so on. So this gives rise to a lot of waste in the memory, right? So everybody is just connected to their neighbors, and as a result, you have allocated memory to connections that will never be there, right? So it's just a waste in memory. So how can we get a better utilization of memory, getting inspired by this small world connectivity in the brain? So what we can do is to basically break this large crossbar into much smaller crossbars that are now, just for local connectivity. So now they're much more densely connected. So you have a better memory utilization. This is actually also what happens in normal processors, right? Like you don't want to have these large memories, because why? Because if you have a large memory, that means that your wires are long. If wires are long, that means you have to pump a lot of energy in order to drive it. So usually in memories, we bank with what is called the banking the memory. So you take one big memory and you bank it into a smaller memory. So it's a kind of a similar concept.
And also for side effects.
Exactly, for parasitic effects. Yeah.
This is bad for many reasons.
Right. So then you can have these kind of local clusters with more dense connectivity. So then you end up with basically these, let's say, small worlds, right, which are highly connected. And now you want to make sure that these can talk to each other. So what we can do is to connect them through some distributed routers. So now you put these routers in between, and you can basically how it now works is that you have these small worlds that now if they want to talk to each other, they have to send their spikes now through these routers to northern, eastern, southern, and well, I guess south and east got swapped, but you get the point. So every tile of this kind of mosaic type architecture now can talk to their neighbors through sending information to different directions. And now we can implement all of these with this resistive memory. And the state of resistive memory inside these computational nodes determines how to do computation. And the state of memory in the routing nodes tell you how this information spreads in the network. So basically, you build a small world graph, which has a lot of memory savings now compared to that big memory because of the better utilization of the memory that we were talking about. So now we have implemented this and it works. Just want to also give you a comparison to the previous just normal recurrent spanking network that I was mentioning. Again, benchmarking it on this heartbeat anomaly detection and speech. And you can see here that using this mosaic architecture for the simpler problem, which is the ECG problem, the accuracy almost stays the same. But for the speech, which has 20 classes, you get a hit in accuracy because now you're constraining the connectivity very much, right? So you cannot, you're telling the network that the neurons can only talk to their neighbors. You're putting a huge constraint on the connectivity, which gives you a little bit of a hit in accuracy, but it gives you a lot of savings compared to the previous case. For example, in the previous case, for the SHD, for this speech problem, we needed about 100 kilobits of memory, but now we need some 30 kilobits with this method, which then also gives you a lot of energy saving. This almost the same amount. This is a log scale, so it gives you almost 3 times because most of the energy goes into reading memory. So basically, there are all these kind of tricks that you can do on basically based on the constraint that you have on the edge, depending on the accuracy that you care about, depending on the resources that you have. If you very much, if your resources are really constrained, then you can, trade off with the accuracy and have better memory savings with, for example, this local connectivity in this architecture. And now to answer Yasin's question again, so you see this accelerator state of the art has 10 microwatts of power consumption, but again, it's a very optimized engineering that was published in Journal of Solid State Circuits. Are there any questions? So it's 12:15. I can go through this online learning part a little bit, and you can just tell me whenever you're tired, and we can just finish it. Okay. So I was saying that online learning or online adaptation is something that all intelligent or biological intelligence systems, right? So you put you put an animal in a new environment and it learns and starts to adapt. And this is important part of the definition of an intelligent system, to be able to adapt to its environment and to the information it receives. So what we mean by online learning, again, is that we do not want to collect a data set. We don't want to go to the environment, start collecting data set and train our network and then, be happy. We want to, keep looking at the environment as the sensor information is coming in and change the structure of our network based on that. We believe that this resistive memory is a good implementation for that, because because of basically these properties that it has, which is multi-states. Because if you want to train a system, you need to have it's good to have more bit precision, right? Generally, for all neural networks, the more bit precision you have, the better it is. And these systems are non-volatile. So let's say if you're on another planet and somehow your battery, runs off, or you're in an environment that there are scarce resources, you don't have to. If you don't have non-volatile memory, somehow the information is lost, right? If you have a power shutdown. And these systems and these devices have internal dynamics, which is good for online learning, and I'll get to that. Now, what are the challenges for this online adaptation? So this is generally a very difficult problem. Why is it difficult? Because now if you want to adapt things online as the information is coming, you need to have a constraint on spatial locality. So your weight update has to only use spatial local information for updates. Why? Because if it doesn't do that, for example, in backprop. So backprop is not it doesn't have a it's not a spatially locally algorithm, right? So it means non-local information for weight update. And that means if you want to build this in a hardware, that means that if you want to change each of these weights, you need to calculate this somewhere and bring it to the synapse, right? And if you want to do that, then your entire hardware is now blown up by wires, because information was not locally available. It means that it needed something that has to be brought to it. And now you need to have a lot of wires that just go around for the synapse to know how to change itself. So your information should be spatially locally available. Now, it should also be temporally locally available, because as the information is coming in, you don't know what is in the future. So forget about future. And about the past, you can't know a lot of information about the past, because if you want a lot of information about the past, then that means you have to have a buffer. You have to keep storing this data to be able to look at a lot of information in the past. And you can't have that, because then that requires a lot of memory, which again, on the edge, you don't have. You want to have a very small system. So this information, whatever weight update you want to do, it has to use a temporal information that is very local in time. And also, you have to deal with limited bit precision. So like I was saying, even these devices, this resistive memory devices that have multiple states, but again, maximum they have 3 or 4 bits. So you need to be able to deal with this. So how I'm just trying to go through these very quickly of some of the solutions that we have come up with to deal with these problems for online learning. So basically, we have now this crossbar array, right? That I was mentioning, which is this basically doing this vector matrix multiplication for us. The spikes are coming in, and these are basically neurons here that are generating the spikes. There is some target spikes that we want, either is rate or whatever your loss function or your output encoding is. You want to get the spikes, compare to this target, generate an error, and then feed it back to this basically your crossbar, which is holding the weights of your network. So if you remember, this is what I was saying about training networks for a spiking network, right? So you have this derivative of the loss function with respect to the weight, which we wrote as the multiplication of three values, which ended up being the error, the input, and this non-differentiable term, which we said we're going to replace by the surrogate function. So now, if we take this second term, which is basically this surrogate function now, if you take a derivative of this, you basically have derivative of this is 0, derivative of that is 0, and you just end up with something in the middle here, which is only 1, so which looks like what we call a box function. So you just look at your membrane potential. If it's between these two values, it's 1, otherwise it's 0. So then as a result, your weight update ends up being basically the error times your input if your membrane potential is between those values. So now I said we need spatial locality. So a pre or an input is available to the synapse locally, right? So you have these synapses like this. These are inputs. So all of these synapses that are related to this input, they have this information locally, right? They have an access to it. Then there's what we need is the membrane potential of the postsynaptic neuron, which are here, which these synapses also have access locally to it. So this synapse has access to this guy, and that's all what it needs. This synapse needs information to this and that, and that's what it has. So locally, it has access to input and the membrane potential of the post. So those two are locally available. What is not locally available is the error. Error is something that you have to get it from somewhere. So what we decided to do was this was a collaboration with Emre when he was at University of California, Irvine. So he had this idea of encoding errors now into events. So now you have this error. If your error is high, you can generate these spike rates that are high, and if you have a low error, you have this spike rate that is low. And events, we know how to send. It's easy to send digital events out. So then we came up with this architecture where you have these kind of neuromorphic or neural computing cores that have basically this crossbar array, and you have these programming cores that they do error calculation and generate events, and they do some kind of asynchronous handshaking with the neuromorphic cores. And as soon as these neural cores receive an error event, they go to the learning phase. They do an update based on the error that they receive, and then they switch back to the inference. And that's how you can do basically online learning. So all of these neural codes are receiving sensory information. They're processing it. As soon as there is an error event that is for them based on handshaking, they go to the learning mode. Based on this pre and the post synaptic information, they update their synapse, and then they go back to the inference mode. Now, the thing that so this was on a spiking convolutional neural network that we trained on a data set that was recorded based on DVS, this dynamic vision sensor camera. So the data set consists of people who have done, left hand wave, right hand wave, clapping, playing a guitar, doing drums, and doing, clockwise hand movement, counterclockwise. So basically, it's a gesture data set. And like I said, it's best for DVS because it's something that is about movement and is not just about something. It's about some action. So in this data set, we have trained this spiking convolutional neural network based on this idea. And because now we're doing error encoding, we have what we can do is that we can choose what is the bound on this error frequency. So if we're again at an environment that we don't have a lot of energy, we cannot spend a lot of energy just continuously updating our weights, we can reduce the event rate. We can put a bound of, for example, 10 hertz, and in that case we will have a higher error in, for example, for this task. What if we care very much for accuracy, and we have the energy to spend, we can, for example, increase the error rate to 1 kilohertz, and then reduce the error. So, for example, this is an example of doing online learning for gesture recognition.
Yeah. Can you change the event rate dynamically? I mean,
Yes.
it's something that can be done.
Yes. Right. So we haven't done that, but I can think of, for example, you can have a feedback system that can look at something you care about. For example, let's say battery level, for example, right? So it just looks at battery level and then it just dynamically changes the bound for error.
It's something that.
Yeah. Yes. Sure. Of course. Yeah.
Notice that if you go from 6.5 to 5.6%, you increase just from 10 to 50 hertz. But then to gain 1 point more, you increase by a factor 1,000 or 10,000.
Right. It has like just not linear, right?
Not so. It's expensive. Because also you increase the rate of the errors and also the energy to communicate that increase, no?
Right. But in normal ANNs, also this, the last percent is always
Yes.
Yeah. It's always the hardest to gain the right.
When you adapt to the new data, let's say, so you are doing online learning. If I got it right, you are forgetting.
Yes. So this doesn't solve the catastrophic forgetting problem. Nothing does. This is just online learning. So that's a whole other thing on its own, right? So this is it basically goes to continual learning, which then has other solutions that people are working on, right?
There are solutions.
Well, from the AI community, right? So you have these the things that I know, for example, is meta learning, right? So you can train these bilayer optimization loop, right? Which is trying to learn from a distribution of tasks. So basically you train the network in a bilayer, so with also hyperparameters on a class of problems, a distribution of tasks. So for example, that's, let's say, one direction. The other thing is this generative models, right? So basically there's also transfer learning. There's a lot of stuff, right? It's not out of the scope of this talk, but yeah, that's a whole new thing on its own.
These things can be applied to this type of.
Not yet. So actually, I just won an ERC grant to do that, basically. Yes. Thank you. So yeah, so it's not it's still a research. Okay. So, all right. So just then just about this temporal locality. So I was saying that there's this window of time that you need for doing updates, and you need this temporal locality. So how can we solve this? So apparently, as it turns out, the brain has a mechanism to solve this temporal locality because of course the brain doesn't have a buffer to store all this information. So what it can do is it has a filtering scheme called the eligibility trace. So what this eligibility trace is about is that, our neurons, the temporal information or the time constant that your neuron has is maximum about 100 milliseconds. So it goes between something like 5 milliseconds to 100 milliseconds. And in the world, when we're acting, our actions times the behavioral time scale that we have is about seconds to tens of seconds, right? And I'm sure in the reinforcement learning tutorial that you've also had, right? So basically, you have to solve this what is called a temporal credit assignment problem. So how is it that our neurons that are integrating information in such low time scale can learn something that is in this behavioral scale? Because by the time that, for example, I'm behaving, I receive a reward or a punishment or something, my neuron has already completely forgot what was the case, because its integration time is super slow or super fast, much faster than the behavioral. So apparently there's this filtering scheme, which is what is called an eligibility trace, which basically filters this, for example, coincidence between pre and the post with the time scale that is in the order of seconds or tens of seconds. And it's this filter keeps this information for much longer until, for example, a reward or punishment or whatever in the behavioral time scale arrives, and then it updates the synapse. And this is something that, for example, has been reported in these neuroscience papers, that there is this filtering scheme. Also, some colleagues from University of Graz, some 2 years ago, they came up with this EPROP learning rule, which is an online learning rule. So what they said is that you can rewrite the backpropagation through time as the multiplication of two factors. One is a learning factor, which is a feedback learning signal, and one is a feed forward signal, which they wrote as an E. And as it turns out, this E it basically acts like an eligibility trace. So you can approximate this exactly like an integrator that is integrating information over time and this learning signal. Now, the problem with this learning signal is that, of course, it also depends on information that is going to come later, which we don't, as I said, we don't have available. And they just decided to just ignore the future terms. Let's say what happens, right? And as it turned out, by ignoring these, it's not like these are ignorable. They're not small, but they just ignored it, or they're not necessarily small. But just by ignoring it, they show that they can solve, some problems. They can, for example, even solve some reinforcement learning problems. So this, it seems like this is a good approximation, at least for small problems. So these eligibility traces seems to be, found in the brain. Also, they help you approximate backprop. So maybe we can try to implement them also on our chips to solve this temporal locality problem. So the way that we know how to create like a long time constant. So the problem is that, if you want to create a long time constant with a physical system, so you either have to have a large resistor or you have to have a large capacitor. And both resistors and capacitors are really bulky. They take usually a lot of space on silicon. And for example, we have used some tricks from this. There's this CMOS process, fully depleted silicon and insulator, or FDSOI. How many of you know what that is? Yeah. Okay. So it's a silicon, it's like a advanced CMOS technology that you can reduce the leak of the transistors. So you can really have small currents. When you can have small currents, you can create, you can have capacitors that charge and discharge very slowly, and as a result, you can create large time constants. So we have been able to, for example, create up to 6 seconds of time constant, for example, using this FDSOI as an implementation of eligibility trace. But as I said, this is not a very good implementation. It's very area inefficient. So what we have realized we can do is to exploit some internal dynamics of a specific type of resistive memory called phase change memory. So phase change memory is basically based on these chalcogenide materials. So you really have this chalcogenide material that is going from this amorphous state that everything is very disordered, because you have this disordered electron doesn't pass. And then you can apply a lot of current to it. This chalcogenide material literally melts and it crystallizes. And because it crystallizes, now electron can pass. So basically, it's again a non-volatile memory based on this that whose phase changes. And interestingly, when this device is in high resistive state, it creates this structural relaxation. So it doesn't like to be in that state physically. And as a result, when you put it in that state, it just starts to drift naturally to a high resistance. And this drift, which basically happens just because of a physical mechanism, is at basically the time constant that we like to implement for eligibility traces. So we try to basically exploit that for implementing eligibility trace. And we saw that we can basically save about like 1 order of magnitude using this internal dynamics. So basically, this is kind of an example of how you can exploit the physics, really physics, for doing computation. And then you also have to deal with the limited bit precision using some tricks, for example, to control the filament better. So like I said, in these oxide-based devices, there's a filament that forms. The thicker the filament, the higher the conductance, the electron can pass better. So if you can control the thickness of this filament, you can control the resistivity better, and you can have you can take more bit precision, for example, out of the devices and so on. Now, I don't want to think then there are other solutions that you can also do for dealing with this limited bit precision. And I basically just say this. You can look at this resource here if you're interested, that we have compared different methods of dealing with limited bit precision. For example, the mixed precision approach, which is something that IBM colleagues have used, which is very interesting, actually. So you have this device that has very limited precision, but you can maybe have a coprocessor next to it that is not always running and is only sometimes running. And this coprocessor can integrate gradients for you. And so basically, you receive these gradients and weight updates. It just integrates it for you with a high bit precision. And as soon as it kind of hits the quantization level of your memory, then you can map this into your low bit precision memory and do learning. Yes, it's over.
I'm so sorry. Sorry, I didn't mean to interrupt you.
Yeah, sorry. Okay, and then we have also implemented this and it works. Just ending with this, which was one question I think Yasin was asking, or so basically we just to compare it with the very conventional systems, we have done this what is called sensory fusion with neuromorphic systems. So basically we are fusing now this vision sensor, it's dynamic vision sensor, with the EMG sensor is the muscle activity. So we encode both into we encode the image in EMG hand gesture. So we had people actually, we collected this data set. We had students in the institute have these hand gestures that you can see on the right. So we had both a camera in front of them, so you can see how the output of the DVS is here, for example, from this vision, from this hand gesture. And then we also had this Mayo armband with 8 EMG sensors that are detecting the muscle activity. And we encoded this muscle activity into spikes. We took the spikes, we combined them into actually a CNN, spiking convolutional neural network. And we ran this on 2 neuromorphic chips, one from Intel and one which is more of an application-specific system. And we compared this to NVIDIA Jetson Nano. So you can see here, just look at the energy delay product, which is basically what we at the end care about, right? So we want a system that has low energy and low delay. So whoever is lower is better. So you can see a comparison, for example, of Loihi, which is, it's microjoule second is about 1, and you see NVIDIA Jetson Nano, which is basically about 100. So you get, 2 orders of magnitude compared to a NVIDIA Jetson Nano for neuromorphic systems compared to the GPU. Yeah, and I just conclude my talk here. So brain-inspired hardware uses these organizing principles. We've used sparsity, we've used online learning and local connectivity. And it's a solution that really has to come from combining, all these levels. Like you really have to understand, physics, and try to understand like neuroscience and algorithms, and kind of combine all of this into a seamless co-design fashion for hopefully more efficient edge systems. Just want to acknowledge people I have worked with, students, collaborators, and also funding agencies. Thank you so much for your attention.
Any questions?
Just I heard about birds trying to predict this drifts that you were talking about for things.
Phase change memory. Mm-hmm.
But you don't seem to need to predict it.
So usually this is a bug, right? This is a problem that people try to solve. For example, by modeling it in their networks while they're training it and so on. And we're trying to use that as a feature. We're trying to like exploit what is happening instead of fighting it in this case.
If you don't know if it's going to happen fast or not,
so we
expose it.
Right. So as statistics, right? Like this drift happens. Okay, there's some variability, but there's some mean value that, let's say, you can count on, and then. Yeah, so your let's say your temporal window changes a little bit, but then you can introduce that into your models.
How many people actually? Because you're using neuromorphic devices for classification of gestures or sounds, etc. Is everyone doing that? Or, is like a small community or?
So right now, I think worldwide, we're probably a community of about 500 people, I would say. It's still not a very big community. It's kind of concentrated in Europe, I would say Zurich, Germany, Netherlands, France, Italy. Actually, we have. I mean, our partners are basically mostly from these countries. But there's like a big center in Zurich in Germany, and Netherlands is also now pouring a lot of money into it. In the US, there are also like few labs. Still not a huge community. There's still it's mostly exploratory research. But I think it's increasing. Yeah. So I would really suggest you to look at this neurotech webinars. So we really try to collect information for people who don't know anything about the field and they really want to start. And this was really the goal of the neurotech project, to try to, like, if people want to join, it's a very confusing field. There's so many disciplines and there's so much involved that people don't know what to do. So we really try to do specifically that. So I really suggest you look at the neurotech tutorials. You don't necessarily need to. I mean, if you have electrical engineering background, it should be enough. I would say.
I have a very general comment questions. Maybe you have already answered since the beginning, because you said that mostly neuromorphic computing is more oriented to edge applications, so not very deep networks.
Mm-hmm.
So do you see that this other field, that is quantum computing, is somehow complementary or is more competitor?
Yeah,
because they are also claiming about the efficiency.
Yes. So I don't know a lot about quantum computing, so just take what I'm saying with a grain of salt. In my personal opinion, from what I know, quantum computing is really good for cloud, right? So for data centers, for high performance computing, reducing energy of those, because basically for optimization, right? So if you want to, for example, use a spiking network for optimization, you need to have these neurons spiking, and kind of find these minimas. And for a quantum system, you just need a wave function to collapse, and that happens immediately, right? Like you don't need to create any samples from any underlying distribution. It just knows and it just collapses. So I think what I again, with my limited knowledge, what I see very promising about quantum computing is really for optimization and for high performance computing. But for the edge, you need something slow, right? Because your information that is coming is slow. You don't need high throughput computing. So for example, I think that quantum computing is really good for high throughput systems, maybe for training. Maybe if you have like big data sets and you want to go through them with high throughput and parallel processing, that's very useful, which is not the case at all here, right? Because you have these really slow neurons that are really just trying to process. So I really see that as a complementary field.